Once again, welcome back to our course on the fundamentals of attosecond science and technology, which we bring to you from IIT Madras and IIT Tirupati. So, we are here in the second week of this course, and that is counting by weeks, but in terms of content organization, in terms of the modules, we are sort of going to close the primer on optics and electromagnetics section, as we have called it, and we are sort of transitioning to the next important module of this course, and I am going to make this transition from this lecture onwards. Okay. So, that is to say that some of you who have taken courses on optics or some related science, you could well have encountered some of the things we are discussing in these lectures. So, for you it could be more a recap than learning things afresh. Whereas, now we are transitioning gradually into the what could be brand new content for this course. So, once again I am here to also remind you about the reference textbooks which I am using as primary material, the books by Born and Wolf, Zheng Chang and Roulier, and also credits to Professor Trebino for his lecture materials and inputs. Now, in this lecture, we will do the following. We will recap the last lecture, the core content of the last lecture and just a little before, so that this whole class today can be as self-contained as possible without asking you to remember too many things from the previous discussions. Apart from that, we will gradually transition into, in this lecture, into optical pulses, how to formally describe them, and in this I embedded a few view graphs of Fourier transforms, mostly their properties, which will serve as a toolkit for part of this course and for a major part of this course actually, and also close with frequency domain description of pulses. It is possible that some of this content could get carried over to the next class too. So, let us jump straight into this. So, in terms of recapping what we did in the previous lecture, so our recap essentially will begin with the application of the multiple beam interference phenomena, which, please recall, we took nothing for granted. We basically explored everything from first principles, that is, what is a wave, to what are light waves, what are optical waves, Maxwell's equations, light and optical waves in 3 dimension, the wave equation in 3 dimension, and so on and so forth, right. So, we really have not taken anything for granted. That is the foundation for what we are discussing in this course. So, given that, we then developed the formalism for treating the interference between one or more optical beams, and we also explored the conditions for interference, observable interference and so on, where we came to the conclusion that for observable interference to occur, we need, among other things, 2 very important prerequisites. The first of which being that the 2 interfering beams have the same, share the same polarization, okay, or rather that part of the polarization, that component of the polarization of the 2 beams which are parallel to each other will result in a pattern for the interference. Okay. And then we also noted that considering optical frequencies, which is the mainstay of this course, optical frequencies that is in the range of 10 to the 14 hertz, 100 terahertz and higher for the purposes of this course, we can observe interference using conventional detectors, provided not only the polarizations match, but also the frequencies between the 2 interfering beams also are identical or almost identical. For the purposes of this course, let us say the frequencies of the 2 beams should be equal. And then we took up this principle of superposition and applied it to the sort of high order. We said multiple beam interference. Let us interfere as many beams as we like, and if they satisfy these two conditions which render the coherence, render the condition between the two, between all the interfering beams as coherent. Okay, we introduced this new terminology of coherence in this course. Then we said if that is the case, no matter how many beams or pieces of these electromagnetic waves, we can sort of sum them up in a way so that we still observe interference between them, and this number of beams could stretch to, in principle, to what we might notionally think of as infinity. And one way of realizing this is the so called Fabry-Perot interferometer. One of its geometry is called the etalon, which we described and studied in great detail, and this lays the foundation for optical resonators in general, right. So, this is the Fabry-Perot interferometer or etalon in a sort of way to summarize what we were working with. So, this is essentially a pair of reflective parallel surfaces. We could also have non-parallel surfaces, but that is going to be a discussion for another scenario where we make optical resonators with spherical end mirrors and so on. But for the purpose of this discussion, let us consider a set of parallel surfaces, and if we realize this out of one solid piece of high quality glass with extremely well defined surfaces as engineering can provide us, then the wave that is either totally transmitted onto the right of the screen or the reflected wave, as the case may be, is essentially a series of multiply reflected beams which sum up to give us the total transmitted or the total reflected beams. And in this case, realize that a few quantities are of immense importance for us in terms of the material and optical properties of the etalon. We will study the etalon in detail, and these principles will also apply in their true sense also to other realizations of the Fabry-Perot concept. So, in this case we have two kinds of reflections and transmissions. One is glass to air, where the coefficients of reflection and transmission for the amplitude of the wave are r and t respectively, whereas the corresponding ones for the air to glass are indicated with primes on top, r prime and t prime respectively for the amplitude, reflection or transmission coefficients. I like to stress the adjective amplitude while talking about these reflection and transmission coefficients, because right as we discuss this, we will also describe or use similar coefficients which are ratios essentially also for irradiances or intensities. But sticking to r t, r prime, t prime, all small case corresponding to the amplitude part of it, we essentially had the goal of writing down each of these constituent beams that are getting transmitted onto the right, emerging out of this etalon from inside the etalon to its outside, which is air. We essentially wrote down all these transmitted pieces of beams in terms of the input field amplitude E naught. So, the first or the 0th pass, which does not involve any round trip inside the etalon, essentially is T t prime times E naught, the initial input wave amplitude, whereas after one round trip we have the coefficient that is multiplying the initial input wave amplitude E naught to be again T t prime, but then r square e to the I delta. So, delta is the round trip phase delay, that is the phase delay that the beam incurs upon making one whole round trip. So, in this case it is the round trip comparing the first beam which came out with amplitude T t prime E naught. The second beam went from right to left, had suffered another reflection and came back from left to right and then exited the etalon, right. So, this round trip cost a phase of delta, and delta is nothing but k, the wave number, which is the magnitude of the propagation vector k, which is 2 pi over lambda, multiplying L. L is the path length that the wave traversed during the round trip. In fact, we should carefully say that this is the optical path length. So, optical path length, as you may have learnt earlier, is the refractive index multiplied by the geometric path length. Okay. So, keep doing this. After 2 round trips, this essentially is becomes T t prime times this factor here r square e to the minus I delta gets twice squared to, that is raised to the power 2 for 2 round trips, for 3 round trips raised to the power 3, but then the beam knows no limits. It keeps bouncing back and forth, provided this piece of glass is literally infinite in its extent, right, all the way until it can make bounces on either side. The beam will keep bouncing, and then it will come out with an amplitude in general of T t prime multiplying r square e to the I delta to the power, say, some m for m round trips multiplying E naught. That will be the amplitude of the transmitted wave. We should also note here that the coefficients t, t prime, r, r prime are all ratios, and these therefore do not have any particular physical dimensions, but these are less than 1. A reflection coefficient or a transmission coefficient is necessarily less than 1. Therefore, we will just skip this. We look at this slide in its entirety, since this is a summary, and if you look at the first attempt that we make towards computing the entire transmitted intensity to the right, that is the first line of terms and equations over here, we have a series, an arithmetic series in r square e to the I delta as the common factor multiplying T t prime times E naught, then each of these successive terms diminishes in amplitude. So, the series must converge, and it converges to the value T t prime E naught divided by 1 minus r square e to the I delta, and it is at this juncture that we introduce the reflectance, which is r. It is actually also sometimes called the power reflection coefficient, right, r, which is the same quantity as little r, but now defined using the ratios of irradiances or intensities. Okay. So, it is r square. This is something you can look up a conventional text on electromagnetics or optics to decipher, that r square is equal to r, as well as given r, capital R, it is also equal to T t prime, because the etalon is lossless, it is perfectly transparent, there is no absorption anywhere. Using this condition, we can show that this is the case, and we manipulated the terms that arise after making the substitutions of r square, little r squared being equal to capital R, then little t prime being equal to 1 minus capital R, and then the total transmittance can now be written in terms of just 2 quantities. One are the reflectance of the etalon, okay, it is one number, it is a property of the etalon, and the other quantity that appears in this equation on the right, which describes the transmittance of the etalon, is delta. Delta is the round trip phase. The round trip phase depends upon k, the magnitude of the propagation vector or the wave number, which is 2 pi over lambda, and L the round trip path. Okay. Then we carry out some simplifications and then express the transmittance in terms of, in the numerator, 1 minus r square, r being the reflectance, and in the denominator 1 minus r the whole square, that is plus 4 r sine square of delta over 2. Okay. So, now we again it is an elegant expression in everything, after dividing the numerator and denominator by 1 over r square and setting 4 r by 1 minus r square to be this new quantity defined as f is equal to 4 r by 1 minus r squared. We then deduce that the transmittance T is this very simple elegant equation. It is 1 divided by, in the denominator, 1 plus f sine square delta. Okay. Remember that f depends only on r. So, it transposes itself into a property of the etalon, into a sort of material optical property of the etalon. It depends only on the reflectance. and for various reflectances we plotted the transmittance as a function of delta, the round trip phase, and as the round trip phase sweeps values all the way from a negative integer multiple of 2 pi to positive integer multiples of 2 pi, we get peaks at whenever whenever delta hits 2 pi or its multiples, and higher the f, ergo higher the reflectance, the sharper the reflectance peak, right. That is the key takeaway from this plot. Remember this. So, that is really sort of iconic plot which should be etched in our minds for the remainder of this course, if not longer. Okay. So, but the point being sort of little maybe experimental or physical note, that is, how do I vary the round trip phase delta? I can vary the round trip phase delta by sweeping the wavelength, that is, my source is tunable and it is sufficiently narrow band, both of which are required to make this realization, or if I were to recreate this plot in an experiment, right. So, we can sweep the wavelength of the source, go from negative values of delta to positive values of delta. Okay, negative values, they are only a matter of reference. So, we cannot really sort of go to negative wavelengths or something like that in real life. So, that is of mathematical interest, but then if I swept the wavelength and ticked off multiples of 2 pi in phase, then I would observe transmittances at these chosen wavelengths. So, what are these chosen wavelengths that the resonator picks? These wavelengths are lambda, at which resonance occurs, that is the wavelengths where the transmittance peaks to a maximum of unity. These are nothing but the wavelengths where the cavity round trip length L is divided by an integer m. Okay. So, the cavity, these are sweet spots, so to say, where L is divided by m. Okay. So, these are the fractions, integer fractions of the cavity round trip will give us resonant wavelengths. Okay. Now, the point is, in order to vary the cavity round trip phase, we can also tilt the etalon and ergo have a fine knob over changing L in minute enough steps, so that we can observe these resonances, okay, reproduce this figure in real life. The other way is to increase the thickness of the cavity, which could also be done by applying some strain on the glass. We can apply it through some kind of piezoelectric voltage or any other new method that you could possibly even come up with. Okay. So, but then the meaning of these special wavelengths at which the transmittance peaks to unity. Now, since delta is linear in 1 over lambda, it is linear in nu, the frequency of the particular light wave that hits the resonance, right. So, if I now plot this, transpose the scale from delta to nu frequencies, okay, then the scale is linear in nu and delta at the same time, and these frequencies at which the transmittance is maximal, and in this case unity in each of these, at each of these resonant frequencies, these are essentially cavity modes. These are special frequencies. These are modes that the cavity likes. It likes to sustain them inside the cavity, right. So, what are these so called modes? So, these modes are frequencies nu subscripted with q. Now, q here is the integer index. It can take values 0, plus, minus 1, 2 and so on, right. So, now if I set the value of q to be equal to 1, then essentially the amplitude of the wave inside the cavity is such that in one round trip, okay, going from left to right and back from right to left, this fits, one round trip fits one wavelength of the propagating light wave. Okay. So, or end to end in the cavity, half a lambda is sustained in the geometry that we are portraying here. In the other case, when you essentially have q to be equal to 2, in one round trip going from right to left and rather left to right and right to left, this mode fits in two wavelengths perfectly end to end of the cavity. In the case of 3, it is 3 wavelengths and so on and so forth. So, these are the resonant modes or eigen modes of the cavity. So, of course, this is concerning the longitudinal aspect of the cavity geometry for possible experts in this class. Okay. Now, is this just something I am talking to you about as a nice problem to solve in a lecture course, or can we actually realize much of this or any of this in the laboratory? Yeah, indeed we can. In an experiment of the sort that that I was describing earlier, if I can sweep the frequency or the wavelength of the light in sufficiently small enough steps, then I can hold a piece of this etalon across a beam and measure the transmittance across the etalon, and then the transmitted frequency while being swept, okay, can be measured in terms of the intensity of the transmitted beam or the irradiance of the transmitted beam using even a very slow detector, then plotted as frequency versus intensity. In the real experiment, you essentially have these eigen frequency modes being transmitted very efficiently. We had a bit of a point to ponder here as to why this plot has an envelope. I hope you thought about it. Otherwise, we will discuss this in one of the tutorials, and I will not belabor that point here because we need to get on with today's lecture. I must, however, make this very important point here, that is the transmittance which we plotted theoretically in the view graph on the right is absolute transmittance, as the theory would have you believe as a consequence of the discussion in this in scenarios like this. That is to say, I am not normalizing anything on the vertical scale, if you know what I mean. It is not that this quantity is all identically either 0.6, 0.6, 0.6 and whatever, right, but I simply divided all this by a common factor to get one here. No, in theory, for the lossless resonator with the reflectivity, with any reflectivity as poor as 5%, as high as 87%, you would essentially get the transmittance unity. So, in some sense, even poor reflectors can make reasonably good quality, good cavities, except for the fact that the quality of the cavity, which in one sense you can have a measure of being the maximum to the minimum transmittance, that contrast will decrease. It is not that the transmittance is going to decrease. Okay. So, that is the important point that we must make. But then if we now compare ideal life to real life, that right being the ideal and left being real life in sort of an experiment, you already see that the measured amplitudes, okay, from mode to mode can essentially vary quite a bit. But this is real life, and let me give away a bit of the answer for why the envelope occurs. You can now sort of figure out in the simplest of terms that the something or some things in the cavity may not be identical for all these frequencies which are resonant. That is to say, you can imagine, for example, that the reflector, okay, could well have imperfect reflection, or the beam is transmitting through a cavity that need not have identical transmittance for all the wavelengths over here. But in this case, most likely it is the source which is having a wavelength profile, but that is something that we can discuss later on. So, in real life, if you do not measure a transmittance of unity, it is because the cavity is not necessarily lossless. You can have finite losses in these cavities. That loss could even have some wavelength dependence. Okay. So, that is about the sort of recap for this lecture.